Right, let's get started. So hello, welcome. Thank you for coming. My name's David. I live in Bristol in the UK. I work at Grafana Labs. So in this session, I'm going to present a case study about how I added distributed tracing to one of our systems, which uses the SOX protocol to communicate rather than some HTTP-based protocol. As I said, this talk should only last about 25 minutes, so not too long. We can go outside. We can go get some fresh air. Oh, yeah. So I'll introduce our system and some of the problems we were facing without tracing, and then we'll look at what tracing is and how traces are distributed across systems. And finally, I'll cover how we solved our issue. So have you heard of, or do you use tracing? Do you use it regularly? A bit, yeah. And how about SOX? You're familiar with the SOX protocol? A bit. OK, so we'll cover it a little bit. OK, so about 2 years ago, we built and deployed a new microservices-based system. The system proxies TCP requests using SOX, which is a protocol for doing just that, for proxying TCP requests. So this is the high-level architecture of the system. There are 4 services involved and a client. Requests leave the client, and they travel through each of these 4 layers until they reach this component, the agent at the end, where the TCP requests are then sent onwards to their destination. As with lots of new systems, when we put the system into production, we uncovered some previously unseen bugs. So we were debugging these with the telemetry we had available at the time, which metrics and logs. And this worked fine for a lot of bugs. We were able to identify some unexpected response in some components, say, update the code to handle that properly, and then redeploy. Some bugs, however, were more difficult to find the root cause for. We needed to see, say, the interaction between 2 components, like the gateway and the proxy, and see what one component responded with and how the other receiving component, like what it did with that response, for example. We needed to be able to correlate logs across these components, which is tricky, when they're all running in different processes. And building this mental model of where a request went and what happened to it was made more difficult by the design of the system. The 4 layers of this system scaled horizontally, right? So traffic was load balanced across these replicas at each layer. Some layers retry requests on error, so you can get multiple branches if you're trying to build a path of a path that the request took through that system. Each layer also has some timeouts when waiting for responses from onward requests, and some steps can have pretty high latency, especially between this gateway and these agents, meaning there are bigger time gaps between requests going out and some responses being logged. The agent component in this system actually runs in the customer's infrastructure. So there's a big gap here in terms of network kind of gap, depending on where their data centers are and where their agent's actually running. We had unique IDs per client in our logs, but not per request, right? So if a client was sending multiple requests in a short space of time or concurrently, it was hard to attribute a particular log line to the logic handling one request to another. So here's one example bug that I struggled with. Right? Our SLO was alerting in one particular cluster. It turned out to be one customer who was making a lot of requests and was having some intermittent but quite regular issue. Requests were sometimes succeeding and sometimes returning with an internal error and sometimes returning with a timeout error. Right? The requests that returned an error were taking quite a long time to respond, around the length of the timeout of one of the layers. Right? So the timeout error makes sense, but it was a bit confusing to be getting these internal errors too. Eventually, we kind of figured out that the rightmost layer in our infrastructure, this gateway, was indeed hitting a timeout on the onward request, and it was returning that appropriate timeout error to the proxy, and it was closing the connection to the proxy. The issue was there was a race condition in the proxy between handling the timeout error and the connection being closed. Right? So if in the proxy we got the timeout error through first, it handled that appropriately and kind of passed it back down the chain to the client. But if we happen to get the connection closed event coming through to the proxy first, then that kind of resulted in an end-of-file error because it was unexpected and the system was throwing an internal error there. So there's one more layer of complexity when I was debugging this, and that was that if errors get back to the distributor, it can try up to 2 more times, right, to get a successful dial. If any of those 3 requests succeed, the response is a success, right? So we only see errors on the client if all 3 of the requests from the distributor fail. So when I was trying to correlate these things together, we were getting some errors in the gateway, but no errors in the client. And it was just kind of difficult to build a strong correlation between where the error was actually happening for the client. Anyway, we fixed the bug by making sure that the timeout error from the gateway was being handled before the connection was closed, right? So we just add a short delay in the gateway from sending the timeout error to actually closing that connection. So when debugging this, I spent a lot of time trying to match logs for the client in each of our components by timestamps and trying to build like a map and a mental model of where requests were routed and what response each component gave. It was quite tedious work, it was quite error-prone, and more importantly, it took a long time to find the root cause. So adding tracing to our system would provide real value in these kind of use cases. We've got tracing in the majority of our systems already. Tracing would allow us to see the full path of the request through all of the components in our system, especially in this one, which is useful in this one when they travel across multiple services. And you can see how long requests spend in each part of the system, as well as any events like timeouts or errors that you want to instrument that happened along the way. Right? So it's perfect for debugging problems like the one I described. However, the issue is that our system communicates with SOCKS and not anything HTTP-based. Right? There's no tracing support in SOCKS. So how do we do this? So first we'll have a brief look at what tracing is and how traces are propagated across networks. So traces are one of the three pillars of observability, along with metrics and logs. So engineers can instrument their applications to emit metrics, logs, and traces to help them understand their system's behavior as it's running. OpenTelemetry's definition of tracing of a trace is that it's the path of a request through your application. Application here can be kind of any application from some monolith through to a complex system of microservices that can be distributed in nature. A trace itself is made up of one or more spans, and a span can have parent or child relationships to other spans. Each span usually represents some operation, like a function call in a system. When you implement traces in your application, you import some kind of provider, tracing provider that is. This provider collects those spans and typically exports them to some trace backend, right, which stores your spans for querying later. Traces are often visualized in a graph like this one with a time axis. And you can see there are 4 spans in here, the 2 in yellow and 2 in orange. There are 2 services here in this example. So the names are bold on the left. You've got a front-end service and a catalog service, and they both have 2 spans each. There's a get/API/tools span, and then a HTTP get span on the front end. And then in the catalog, you can see a get/API/tools and a select. Right, each span has a duration next to it, so that shows how long the request spent in each of those spans. So let's have a look at what's stored inside a span. Right, this is OpenTelemetry format for tracing, which is what we use at Grafana. And here's the span from the first span from the previous image, the top yellow line, in JSON format. Right, so we can see there's a trace ID, which is a unique identifier, which will be used in all the spans for that trace. There's a span ID, which is the unique ID for this particular span. There's a parent span ID, which is empty here because it's the root span, it's the top level. Right, so if any of those child spans would have their parent span ID in here. I put trace ID and parent span ID in bold here because they make up something called the trace context, right? And the trace context is all the information that a trace backend would need to be able to figure out which trace and where in that trace a given span would live, right? And that we'll use that later, and that's kind of what we use to propagate traces along to the next service. Spans also have a name, they have timestamps to start and end, so you can see how long it took. You can add attributes to a span, and that's just up to the engineer to decide what attributes they want to add. It has a status property, which is kind of like a summary of whether the kind of logic within that span succeeded or failed. And you can add a message there if you want. There's also events, which I haven't got here, but those are like discrete time-stamped events, kind of like logs that you can also add to spans. This contains all the information that trace backends require to create those trace visualizations like the one on the last slide. So that covers traces and spans, but what is distributed tracing? Distributed tracing refers to tracing requests when they travel across multiple services, for example, via a network call. Right? A trace context is passed along as part of that network call, typically as HTTP headers, and the receiving system uses the trace ID and the parent span from that trace context to associate the spans that it generates with those from the previous system. OpenTelemetry defines this concept as context propagation. So if we don't propagate trace context, we don't see an accurate picture of what happened. So these are the 2 services that we saw in our trace visualization. We've got the front end and the catalog, and these are the spans that they generate. So if you don't propagate the trace context, what you get is when the front end generates its spans, it has a trace and those 2 spans, and then It makes the network call to the catalog, right? But when the catalog service receives that request, there's no trace ID or parent span ID in the metadata. So it starts its own trace with its own root span, right? So when you try and visualize that request, it actually materializes as two separate trace IDs. And that's not particularly helpful for trying to understand where that request went through all of your services. So when you add context propagation, when you make that request, the trace ID and the parent span ID are propagated along to the catalog, and it can extract those out and use them. So when it's exporting its own spans, it includes that correct trace ID and the parent span ID, and then it can all be fitted accurately into the correct hierarchy. For HTTP-based protocols like gRPC and any HTTP request, we put the trace context into a header on the request, and that's how it's propagated. The default format for those headers is this W3C trace context specification. This format uses two headers, right? It has a trace parent header and a trace state header. The trace parent header contains all of the information that the receiving service needs to associate these spans together. Right? And the trace state header is not really relevant for this session, but what it's used for is if you have services that use different tracing providers, right, that kind of generate different trace ID formats, you can put them both into here to kind of correlate those traces together, right? So if your one service is generating some trace ID in this Rojo format, and another one is generating trace IDs in this Congo format, you can kind of put those two together to show that it's all part of the same trace, really, and they can all be correlated together. But let's look at that trace parent header in a bit more detail. So what's it got in it? Right? It's a fixed length. It's a fixed length header. Well, each field is a fixed length, and they're all separated by hyphens. We've got a version field, which is always set to 0 for the current spec. There's a trace ID then, followed by the parent span ID. And then it has these flags. And there's only one flag defined at the moment in the spec, and it's this sampled flag. And that denotes whether the caller, the previous service, sampled the existing trace data so far, right? And the idea here is meant as a guide to let the current service decide whether it wants to sample this given span or not. Right, so typically with tracing providers, we can't sample all the spans. If you try to kind of export all of the spans, it'd be too expensive to store. So you normally pick a percentage. But when you want to see a trace, you want to kind of see you want to store all of the spans for that given trace, and not have something called fragmented traces, which is when you only have a proportion of those spans stored, right? So what this flag will allow you to do is it tells you whether the previous services have kind of sampled this span, so you can decide whether or not to continue sampling it or not. And it's just a guide. So we've seen how distributed tracing works and what information is transmitted in this trace parent header. So where are we going to put this header in our SOX-based system? So a brief introduction to the SOX protocol, right? It's a protocol for proxying TCP requests to some arbitrary address, right? Its last RFC update was in 1996, so it's been around for a while. And what you could do is from a compatible client, for example, curl, you can proxy requests to a SOX server, right? So if we add something like this --SOX5 flag in curl and give it a SOX server address, what it will do is it will wrap the actual destination address, in this example, httpbin.org, and it will proxy that. It will send that kind of SOX request over to the SOX server on localhost 1080 here. Upon receiving that request, the SOX server proxies that SOX request over to some SOX proxy server, which is at an address that it's configured to know about. And when that SOX request reaches the SOX proxy server, it unmaps the actual destination address and dials that address from wherever it is. And if it manages to get a TCP connection, that's returned to the client. Right? SOX proxies, you could just use a HTTP proxy instead, for example, but they're useful in cases when you need to handle a wider range of traffic. So in our use case, we want to be able to proxy HTTP traffic, but also SQL traffic or any kind of TCP-based traffic. So for that, SOX is a bit more appropriate. So where can we put our trace context? This is what a SOX client connection request looks like. Right? This is the message that's sent to the SOX server. There's a version, which the current latest version of SOX request is 5. There's a command, of which there are 3, and we use connect. And then there is a reserved byte. And then there's the address, and that's in our example, would have been httpbin.org. It can also be an IP address, version 6 or 4. And there's a port. Right, so there's not really any room for adding metadata into this part of the request. SOX does, however, have optional authentication methods, and one of those is basic auth, user password. Right? We don't use SOX authentication in our use case. We establish trust between our components using MTLS. Right? So we don't use this for authentication. We do actually use the ID field here for some internal routing logic. Right? So, but that does leave this variable password field empty. Right? So that's a candidate for where we could put the trace parent header. So the password field can fit 255 bytes, right? ASCII encoded, or ASCII characters encoded in UTF-8 use 1 byte each. The trace parent header, along with its key and the equal sign, is 68 characters, right? So it fits. So we've got somewhere to put the string, and now we just have to figure out how to get the value from the program context, like the trace context, sorry, from the program context, and put it into the request, and how to get it out again. So OpenTelemetry has a spec for this, right? They're called propagators. Propagators are types that send some kind of state, things like trace context, to the next service. Propagators use something called carriers to transfer the context to the next service. The propagator here will take some state from the program context, right, the trace context in our case, and inject it into a carrier. And that carrier is then written into the request and sent to the next service. In the receiving service, the propagator, or the metadata, the trace context is parsed from the header into a carrier, and then the propagator can use that carrier to extract the trace context and put it into the program context in the receiving service to be used onwards. For HTTP requests, there's a header carrier, right? So the propagator can extract that trace context from the program and write it into a HTTP header object, and that can be written onto a HTTP request and sent along. And equally on the other side, we can just extract that header, and then the propagator can use that HTTP header object and inject the trace context into the program scope in the receiving service. So we want a similar thing, but we want it as a string rather than HTTP header. So we can write it into our password field. So OpenTelemetry provides another carrier type, the map carrier, which stores state in a map of string key value pairs, right? So we can use that. So some brief code snippets. So our service is written in Go, so that's what these snippets are. Right, so this function at the top, trace context to string, is what gets the trace context out of the program context, this context.context object here, and returns a string. So what we can do is use some of the types from the OpenTelemetry propagation SDK. So we have this trace context object and a map carrier here, and we call a method on the trace context object which takes the program context and the map carrier, and it takes the trace context out of that program context and writes it into the map carrier. And then we can just go and extract that particular key that we want from our map carrier and write it to a string. And then in our logic, where we're actually kind of making the SOX request, we can just get that string and put it into the password object on the auth object there. On the receiving end, we can use the same types, right? So the SOX server will extract the password string from the request, and then we pass it to this parse map carrier. What that does is goes and actually gets the value of the trace parent key there and sets it into this map carrier that we've got, and it returns that. So when we're trying to extract from the map, we parse the password into a map carrier, and then we use that in this trace context object that we've got, and then we can use one of the convenience methods on that called extract, which extracts that trace parent header into the program context, and then that program context is used for any onward logic in that service. Well, that's all we needed, really. I mean, this is a resulting trace from our system. It shows, well, the text is quite small, but it shows that it shows a trace which includes spans from the distributor, the proxy, and the gateway components that we saw of the service in the correct hierarchy. The implementation was quite straightforward in the end, but it required some understanding of how context propagation actually worked and some research into what fields we had available to us in our requests. These traces have been really useful in debugging problematic requests in the system. So that's it. I hope you found this interesting. Tracing is not just for HTTP requests, and maybe you'll have a use case like this when you can implement distributed tracing as well. My email address is at the bottom if you want to get in touch. Thank you very much.